So now that we've covered SN2, SN1, E2 reactions, we're going to cover our last type of reaction that is similar to this, and that is the E1 reaction. After that, we'll work on practice and integration of the rules and deciding which type of reaction applies based on the reagents and the solvent present. So for the E1 reaction, this can occur with tertiary alkyl halides and secondary alkyl halides. And the reason we're limited to tertiary and secondary alkyl halides is because we are going to go through a carbocation intermediate. And the rate of reaction, similar to the SN1 reaction, because it goes through a cation, the rate limiting step is the formation of the cation, and the rate of the reaction is dependent only on the alkyl halide. The solvent used does not affect, the solvent and the nucleophile do not affect the rate of reaction. Let's see. Okay. For E1 mechanism, I would say that a good rule would be that heat favors elimination. So oftentimes when they propose and they ask you if it's an E1, an SN1, an E2, or an SN2, and you're trying to figure out what the possible product is, if there is heat at the reaction applied at the reaction arrow, then it is probably an elimination product. Okay, so for the E1 reaction, the alkyl halide, the first step is that the halide departs, forming the carbocation. So here we have our 3-carbon carbocation that occurs when the bromide is kicked off. Then once we have the cation, a nucleophile will remove a proton from the carbon adjacent to the positively charged carbon. So here water is acting as a base, removing a proton, and then the bonding electrons, the sigma bonding electrons, are used to make a pi bond. When this pi bond is made, the positively charged carbon will then have an octet, and we will have our final molecule, an neutrally charged alkene. Now, you might ask, how does a weak base remove a proton from an sp3 carbon? The presence of the positive charge greatly reduces the pKa of the proton. Because the carbon has an empty p orbital and a positive charge, remember that carbocations are stabilized by hyperconjugation, which is the sharing of electron density from the carbon to hydrogen bond of the adjacent carbon. And because the positively charged carbon is stealing electron density from its adjacent carbon to hydrogen bonds, it is making that bond weaker so that the proton will leave more easily. And therefore, and whenever we make the bond to hydrogen weaker, we make that hydrogen more acidic. E1 reactions are regioselective. What that means is that we can make multiple products, but we will have major and minor products. The major product will be the Zaitsev product, the product formed from the most stable double bond, and the minor product will be the product formed from the least stable double bond, or the anti-Zaitsev product. The more stable alkene is obtained by removing a hydrogen from the beta carbon that is the most substituted. So for our alkyl halide, we have 3 beta carbons. Wow, no eraser allowed. 1, 2, 3. And those beta carbons are, the methyl groups are primary. Boy. And the CH2 group is secondary. So the CH2 group has the fewest hydrogens and is the most substituted. And so the major product will be formed from the carbon with the halogen making a pi bond to the secondary carbon. So the secondary carbon will lose a hydrogen and the carbon with the halogen loses the halogen, and we gain a pi bond between those two carbons. From CH2 to CH and CCl to C. For an E1 reaction, the more stable product is going to be the major product because it has both the lowest activation energy, because it has the more stable transition state with the pi bond forming in a more stable position. It also has the lowest energy product. So that will be the more stable alkene. For E1 reactions, the stability of the leaving group is the same as for SN1, SN2, E2, and E1. The best leaving group is the one with the weakest bond, and that is iodide. Strongest RX bond. So the most reactive has the weakest RX bond, and that bond breaks the most easily, and the strongest RX bond is the least reactive because the bond is the hardest to break. Competition between E1 and E2 is going to occur, but there's also competition between SN1, SN2, E1, and E2. Okay, so let's talk about this competition just between E1 and E2 to begin with. Primary and secondary alkyl halides tend to undergo E2 reactions because they form less stable carbocations. They're unlikely to undergo E1 reactions. Tertiary alkyl halides undergo both E2 and E1 reactions at the same time. Fortunately, usually both reactions favor the more stable alkene, and so both E2 and E1 would lead to the same product. But because both reactions are occurring simultaneously, the true overall rate of reaction considers the rate both of E2 plus the rate of the E1, because they're occurring together at the same time, and some of the product is from E2 and some of the product is from the E1. For tertiary alkyl halides that can undergo both E2 and E1 reactions, we know that the E2 reaction is favored by a high concentration of a strong base. So when they say strong base, they're usually indicating formal charge. Examples of strong bases in this case could be amide, hydroxide, alkoxide ions, which would be basically an alkoxide is a deprotonated alcohol. And an E1 reaction is favored by a low concentration of a weak base. So weak base in this case usually means a neutral molecule such as H2O, ROH. Okay, so those are weak bases. Anti-elimination. For an E2 reaction, anti-elimination is preferred. So that means that the base removes the proton on the opposite side of the molecule, or 180-degree angle to the X. So basically, we would call that anti. Do we have a special name for that? Okay. This requires is a staggered conformation if you're to draw the Newman projection. So that the hydrogen and the X are 180 degrees apart by Newman projection. Syn elimination is sterically hindered and less likely. It requires a frontside attack. Staggered conformation with the hydrogen and the leaving group anti is evidence of a backside attack. The backside attack achieves the best overlap of interfacing orbitals and avoids repulsion of the electron-rich base with the electron-rich leaving group. We know that the E2 reaction is regioselective. For the more substituted alkene, we always get two products from the more substituted alkene, the E and the Z. And we recall from chapter 8 that the E isomer is always more stable than the Z isomer. And so the major product is the trans more substituted alkene, followed by the cis more substituted alkene, and then the less substituted alkene. So let's write that out. Major product then the intermediate minor product is the cis, or the trans, or the E isomer for trans or E, and then the cis or the Z isomer of the more substituted alkene. Is the intermediate minor product. And then the minor product, the one that we have the least of, is the less substituted alkene. If one is possible to make. Okay, the alkene with the bulkiest groups on both sides of the double bond the alkene with the bulkiest groups on opposite sides of the double bond is formed in greater yield because it is the more stable alkene. Anti-elimination. Anti-elimination is when the hydrogen and the bromine are anti to each other. It's most obvious in the Newman projection that they are anti. And the most stable alkene is going to be formed when both the hydrogen and the bromine are anti and the two largest alkyl groups are anti. So if you notice on the figure at the left, we have ethyl and CH3 anti at the same time as bromine and hydrogen are anti. And so that would be the most stable conformation already, because the two largest groups, alkyl groups, are 180 degrees apart and will not have steric hindrance. But if you notice in the figure to the right, bromine and hydrogen are still anti, but the alkyl groups are in gauche. Remember the conformation called gauche. And this conformation has a lot of steric strain. Now, the anti-conformation leads to the E alkene, the more stable E alkene, when the two largest groups are anti to each other and the bromine and the halogen are anti. But the figure at the right, which is anti-bromine and hydrogen but gauche alkyl groups, leads to the Z isomer, and that will be less stable. Okay, and just again showing that the more stable product is easier to form. It has a lower activation energy, and it also has a lower final energy for the product. Okay. Whew. The major product of an E2 reaction occurs when the two largest groups are anti, and this is a topic that is just going to be stressed. Obviously, this is several slides covering this, so you have to remember that this is the case, and that is because of steric strain. Atoms encroaching in other atoms' electron clouds is less stable and referred to as steric strain. So the steric strain for the Z isomer is much larger than the steric strain for the E isomer. Then the other thing that I have drawn here, someone asked in a previous class, why doesn't it form a double bond to the methyl group? And that is because we used a small base. So the base in this reaction is relatively small, ethoxide, and they asked why not form a double bond to this beta carbon. And in order to form a double bond to that beta carbon, we would need what we call a bulky base. such as T-butoxide. Which can be written in shorthand as OC parentheses CH3, 3 CH3s. So what that means is that 3 methyl groups are bonded to this carbon, which is bonded to an oxygen that is negatively charged, okay? So this would be an example of a bulky base. And because the base is sterically hindered, it cannot abstract a proton from the beta carbon that is more substituted. Whoops, I need the highlighter. So we have our secondary beta carbon and a primary beta carbon. Those are our only 2 options for forming a double bond. The major product with the small base given, the ethoxide, is to remove a proton from the more substituted beta carbon. And I was going to use a pen for that, so eek. Red pen, unfortunately. Red, okay. From the more substituted carbon. But this bulky base, what the bulky base would do is to remove a hydrogen from the less substituted beta carbon because the base is sterically hindered. It cannot approach the more substituted carbon because the more substituted carbon is more sterically hindered. So the bulky base always removes a proton from primary carbons, preferably, if possible. And if there are no primary carbons, then a secondary carbon. And so the bulky base is what would lead to this product. Only with a bulky base such as T-butoxide, which if we draw out looks like guy. So people used to say that the bulky base looks like an angel with a halo, but I don't see it. I just see a cross with a negatively charged oxygen. Okay. When only one hydrogen is bonded to the beta carbon, the major product of an E2 reaction depends on the structure of the alkyl halide. So we can get multiple products. We need to have for E2 anti-hydrogens and bromine. There are 2 occasions where bromine and hydrogen can be anti when we draw the Newman projection. And the most favored product will have the largest groups, E. So that, for example, the largest group on the carbon, at the left is the benzene ring. That's what C6H5 means. So wait. Whoops. So just think of this as being this molecule attached to the yellow carbon. And the largest group on the carbon at the right is the methyl group. So when those two groups are anti to one another, as indicated by one being on a hatched wedge and one being on a solid wedge, then that is a stable conformation. The other conformation will be the Z isomer, and that will be the minor product. And this conformation occurs. Let's evaluate. Our carbon on the left has our largest group, the benzene ring, on a hatched wedge, and the carbon at the right has the largest group, the methyl group, on a hatched wedge. And so that would lead to the Z isomer, which would be the least stable. So the most stable comes from these two largest groups being anti when we have anti-elimination of hydrogen, and the least stable comes from the two groups being cis, or in the Z conformation. Okay. When only one hydrogen is bonded to the beta carbon, for the E reaction, we're going through a carbocation, and anytime we go through a carbocation, we can make both the E and the Z isomers, but the E isomer will still be the more stable alkene and will still form as the major product. So in that case, what we have is at the positively charged carbon, we have this empty p orbital and a methyl group, and they are adjacent, and so we have this methyl and this ethyl group. At the adjacent carbon, there's only one beta carbon, and so what we're looking at is the when this hydrogen is removed, is it easier for the base to take this hydrogen from to form the E product or the Z product? And it depends on the orientation of the largest groups. So what are the largest groups? Ethyl or methyl for that carbon, and ethyl is the largest group. So the blue is larger. And then on the other side, the larger group for the removal of that beta hydrogen is this blue group. And the yellow line is where the new bond will form. So the most stable conformer will have the two largest groups on opposite sides, and these two small methyl groups on opposite sides. And that gives us the E isomer. And so that in the transition state, what we have in this case, if we were to draw the Newman projection, what you would have is, if the front carbon is the cationic carbon, we would have an ethyl and a methyl group and a p orbital, which I'm not going to draw. And then for the back carbon, the most stable conformer would have the ethyl groups anti, and I'm calling them ethyl because they contain 1, 2, and 1, 2 carbons. And then a methyl group, the two methyl groups are also are they anti or not? Not necessarily. On the back carbon, we have hydrogen and methyl, and let's see. The hydrogen is shown as going back, so that would be over here. And the methyl is shown as coming forward. This should be ethyl, and erase. All right, so ethyl. The methyl is coming towards us on the back, and the methyl is drawn without specific orientation on the front, but we can put it here. Okay, so that would give us our Lewis structure, and then we would have our p orbital is over here. And it's going to actually go through both sides. So when this hydrogen is taken off, the bonding electrons here will collapse into this side of the p orbital, but that gives us the anti-conformation or the E conformation of our two big groups, ethyl and ethyl. Whew. Yes. I like this picture better. Okay, summary of stereochemistry of substitution and elimination reactions. For the SN2, only the E inverted product is formed. So if there is a chiral carbon, the enantiomer, RS, that we have in the reactant will be the opposite configuration in the product. So if it's R in the reactant, it will be S in the product. And if it's S in the reactant, it will be R in the product. That's SN2. For E2, both E and Z isomers are formed with more of the stereoisomer, which has the E conformation, unless the beta carbon from which the hydrogen is removed is bonded to only one hydrogen, in which case only one stereoisomer is formed. The stereoisomer's configuration depends on the configuration of the reactant. Both stereoisomers, R and S, are formed for SN1 reactions, and which one is slightly in higher yield depends on which would have the inverted configuration. Whichever of the two isomers, RS, results from the inverted configuration will be present in slightly higher yield. For the E1 reaction, both E and Z isomers are formed, with the E isomer being formed as the major product. E2 elimination from six-membered rings. We're going to talk about that next. It has some special rules because of the restriction of rotation in a ring.